Pause, stop recording.
Now we're good to go.
We're good to go. Okay. Wow. Okay. For those of you who are not seeing us for the second time, and this is your first SAC Zoom meeting, welcome to the circus. I'm Tom Curry, the president of SAC, and I will be here to entertain you with my inability to do electronic stuff. I used to work at a place that had a 35-year-old that did all of my electronics for me. He knew that stuff. He introduced me to my BlackBerry that long ago. So that's the way I learned it. Can you see the agenda?
No.
No. Okay. Interesting. We're back to that again. Okay. Once again, take that off. Go to share screen and go to agenda. That's the one I want. Now you've got it, don't you?
Yes.
Okay. The housekeeping, the Q&A tab. If you have questions for us, down at the bottom of your all's participant screen, you should be able to have a tab you can click on to ask us questions. And then the chat screen, you guys back there can talk amongst yourselves, typing out your comments about how you don't want me reelected, please. I mean, for president next year, come December when we have elections. So just kidding, I don't mind. You know, we all have to learn this somehow.
Well, this year shouldn't count.
This year shouldn't count. What are you talking about? I had 3
Give me more years
before we went tits up. I'm sorry. And only the presenters are visible on the screen. And we cannot hear the participants, so you can mumble amongst yourselves. That's why I didn't really tell you all to shut up and sit down, because I don't know what you're doing, really. Those of us who are presenters and commentators, we're the ones talking and listening to each other, so we're hoping that at least we'll entertain ourselves. I hope this will be entertaining for you guys too, but your comments will let us know. The next meeting will be October the 2nd, and we don't know who the guest speaker will be, but we have some that have agreed to our circus. So we'll start off with some of the background information that we talked about in the past meetings. Paul, I don't know if you had heard this before tonight, but La Paz County has bought 4,000 to 5,000 acres from the BLM, including the Hovatter or Salome Emergency Airfield, for a solar development. And in talking with D.L. Wilson, one of the supervisors for La Paz County, he's the one that actually contacted me to let us know. He's also an amateur astronomer, so he feels our pain. But the company that's doing the development work, they're actually on board and working on the geotechnical access roads and the regulatorily required cultural investigation out there. So I was hoping that they would be dragging their feet, not getting anything done for the next year or two, and we could possibly get a memorandum of understanding with the county to use the property for our events. But DL said that's just not going to happen. He says that they're too far along right now. So if you were to drive out there, you might see survey stakes. Who knows what's out there at the airfield. So, Paul, if you know any other places, and any of you other participants, listeners, know of any other locations that would be good for EVAC and SAC weekend events, please let us know where we might be able to get somebody to deliver portalets and have enough flat space that we could set up 100 different telescopes. And with that, let me see if I can pull up, I guess, the first. Presentation will be a quick one for me. Let's go backwards. It's called Winners and Losers. This is what I did during the start of my COVID experience. Actually, not the start, it was just last month. A week ago, or 2 weeks, 2 weeks ago, and then the week prior to that. So the winners and the losers. And this is about beginning astrophotography and just getting out and looking at stuff. We've had a lot of comments by people talking about, well, hey, whatever happened to just observing? And then on this new SAC forum, I have been seeing some absolutely Hubble quality astrophotography that blows me away. It's just stunning stuff. But the thing about it is how long did that one photo take? And I know that Drew's going to be talking about that. But here's the simple stuff. Using my DSLR, a Canon T7i, connected to either of my two telescopes, my 8-inch Schmidt-Cassegrain, or my 9.25 Celestron that I just got, that I'm hoping to figure out how to use my ZWO and my, what's the other device that Star Arizona hypes? Hyperstar, that's it, Hyperstar. So I have just finished an eye test, or a eye appointment with my long-standing ophthalmologist, and she says that my vision is now 20/30. I've got cataracts building, but they're not bad enough. So normally when I see a globular cluster in my 8-inch Schmid, it looks nothing like this. This is a 30-second exposure with my DSLR, probably ISO 16 to 3200 for 30 seconds. And you can see a little bit of star tracing in there, but to me, this is so much nicer than trying to see that little fuzzy thing and ramp up my magnification to the point that I have a problem because I'm wearing glasses. I don't get the eye relief. I can't really get in close, and it's just a pain. But the DSLR, for those of you who are starting off, it's just a great way, or if you're just an old fart like me, being able to see things. So I will go, and in an evening, I'll be able to see 50 different items up close and personal with the DSLR. And I love globular clusters. They're just so cool. I just think they're just the astrophysics. I'd never heard of them before I came with the club, and then people introduced me to them. Omega Centauri, of course, being just the all-time favorite. But these are the types of things, playing with my exposures, just pulling in stuff and being able to see in just brief moments much better than looking through an eyepiece. Again, you're going to see that I've got a lot of graininess, and my exposures sometimes get a little too long. My SCT doesn't track quite well enough to do long exposures. And then looking at those really small planetary nebula, this tiny little blue dot, I forget which one this is, but I was out a couple weeks ago, and I went through a whole series of, on my list of things I just wanted to look at and get a picture of. And it's just nice to be able to pull them up. And I'm not sure if this is M57, the Ring Nebula, or just another one of a similar structure. The Saturn Nebula, I just think it was just real cool being able to pull these up. It's just like having enough magnification and clear enough sky and dark enough that you can see Uranus. It's just, wow, blue. It's so cool. And then you get a nice just time exposure from the Canon off the telescope, and you can see the Andromeda galaxy coming into focus along with the, I presume this is the double cluster in Perseus, but then just seeing the Milky Way and getting a decent shot. It doesn't have to be Hubble quality, but it's a lot of fun. And playing with the exposures, and of course getting it on your computer, then you can monkey with it and change some stuff. Then you get the panoramas. Last week at EVAC, they had an incredible astrophotographer that did the types of photography that I think we'd all love to do. This is up at the Meadows north of Happy Jack. Of course, the light dome of Camp Verde or Phoenix, I'm not sure which it is actually, but then you have Jupiter and Saturn. So it's just really nice. Then, and now here are the losers. The next week we go up there. There are 3 of us together, and we set up, and we've waited out all the clouds all evening long, and we're thinking they're gone, and no. So we get a lot of gaps, and we can shoot some things, but you've got to be quick, and it's like, daggone. So here you go. again, you've got Jupiter and Saturn. Hey, that's okay. If you shoot them quick, you can see them. Then you can see a little bit of Scorpius probably. But you get some nice shots. So we're not wasting our time entirely, although we were frustrated we weren't getting to see anything through the scopes for a long time. And then all through the evening, this is the same stuff we were seeing. The next night, hey, it was even worse. Oh my gosh. All afternoon long, we were watching the clouds come in, and then off in the distance, the thunderstorms and the lightning. And I said, wow, we could hear it. Oh man, rumbling pretty nice. And this, you can see the field here where we're at. And well, luckily it's far enough away that we don't have to worry about it too much, I guess, unless your mother's there, and then she'll tell you to get the hell inside. But there were some pretty spectacular lightning bolts going on. And then this is to the north. And this was closer, much closer. And you can see here, I've now tarped my scope, and I'm about to get the heck back to my vehicle, get inside with all of the insulated tires, and hopefully be safe again. And that is what I did. So let's see. Brew, do you want to pull yours up now?
Oh, okay. Let's see.
Let's see.
I do that. Oop. Oh.
Do I need to hit new share?
Something like that. It says this is going to stop your screen. Oh. Share.
Yep, there we go. You got it, I think.
Is that up?
You're up. Now you just go down and get the little screen, and you know the drill.
Okay. Okay. So this is just three things I was messing with that I thought were kind of different. So first was I started getting into this planetary thing. I've never done planetary imaging. So I thought, well, you know, what the heck? I was thinking about some things. What I hope to do is planetary, and then maybe I have in mind, maybe I can do some of the very small planetaries with this thing. I don't know. So I've got one of these little 290 cameras and stuck it on the back of my Celestron. And so I'm using the Spire Capture free software to grab the video, this auto stacker to stack them. It's got a million options, but once you get used to it, it's actually very easy to use. I'm doing a little bit of adjustment. Well, I'm over adjusting at the moment in PixInsight. And then there's this cool thing, WinJupos, which I think has got an interesting thing. So this is kind of one of my things I did randomly. And then at the moment, I'm just in the mode of experimenting, trying to do a whole bunch of these. So it did 7,500 frames. You do a sub frame of the frame so that you can get a whole lot more frames per second so they can come in. And I stacked the top 20%. So in this case, like 1,500 frames here roughly. And then let's see. So this is the basic image. That's after stacking. And then this is after I've over-processed in PixInsight because I don't know yet what I'm supposed to be doing there. So I kind of been doing stuff. Now, when you do Jupiter and a lot of the planets, they spin too fast. So you can't do, you know, I'm used to doing my 15-minute exposure. So you can't do that. You need to go 60, maybe 90 seconds, and you get that many images. So what you can do is create several images, each of them like a 60-second thing. This WinJupos comes out, it's another free software. It comes out of a project where I guess people take images of Jupiter and send them in somewhere, and they're collecting data on Jupiter. So they measure all kind of things about how the clouds are moving, and I don't even know what all. But one of the things it does is it does this derotating thing. So you can take that's several images, and it kind of derotates the planet somehow, and then you can put them back together again. So you get less noise, better detail. So this is kind of an example. Here was a 90-second stack, and then here's another 90 and another 90. And if you can tell, the red spot here has moved across a little bit on each image. So this is just a regular stack, very hardly any, a little bit of processing, but not much. So 3,400 frames each. All right, so I do these three. And now when JUPOS is going to do is take this first one and rotate it to the right a little bit so it lines up with this one. Take this one, rotate it to the left a little bit and line it up, and then you combine them. And I don't know if you can tell through this. You can see there's noise up here, kind of speckly, whatever noise. And on this one, that's much reduced. And in theory, I should get, if I could learn how to focus this thing, I should get much better definition as well in what it does here. So this WinJUPOS is kind of a cute thing. I can't understand at all how you would back rotate this thing, but that's what they do. So anyway, so I'm playing with this. I can't figure out how to focus the thing at all yet. And apparently seeing is terrible where I am. But it's a start. Like I said, I've not done this before, so we'll see how it works. Oh, and now there's another thing you can do, which is kind of cool. You can take several of these images, and this was just a proof of concept. I got some bad images and I tried it. And there's another free program, PIP, I guess it is. And you can build, this is a GIF. So it takes your images and stitches them together and makes a GIF. Now my GIF is goofy because I was experimenting and whatnot. So there's a glitchy thing in the middle of this because I missed some images. But you can see, you can get an image of the planet rotating by taking a number of images and putting them together in this thing. So that was kind of a cool thing. All right, the next thing, M27, I went back, I do this regularly, it seems. I go back to data from several years previously and redo it. As, for example, PixInsight comes out with new tools, I read about a new processing technique or whatever. So I go back and I redo images. So in this case, this was some data from several years ago, and I didn't like the way it came out. I never did like it. Normally when people do M27, they're doing like a couple minutes or something, maybe not even that. And I was doing 15 minutes because I wanted to get there's this nebulosity that gets around the planetary. And here you can see there's this extra stuff around the outside over here and through here that you don't normally see in these images because you got to go deeper to find them. The thing comes out real pink. It's not the normal red and blue that I want to have. This part's kind of showing up very nicely. So I'm getting pieces that are good, but it was just too light. I didn't like the way it came out. So I was doing some other stuff and come to figure out, oh, and this is when I added H alpha, and you can see it's like white in the center. I mean, it's just too light. So I was futzing around with some other stuff, with some planetary nebula stuff. And I learned that normally when we do images, this is what they look like. And then you have to stretch the heck out of it to get it to show up to actually be something here. So M27 is kind of sitting in the middle here. So in this case, when I did it, because I'm doing these deeper than normal images, it looks like this as a starting image. And maybe you could see the dumbbell is actually already showing up here. Not much, but it's distinctly showing up. So what's happening is the data is already shifted over more than normal. So when you do the normal typical stretch that you would by default do, it overstretches. So these images are coming out too light because it's overstretching the histogram too much. So this was the original. This is kind of what it did with the standard stretch. And then when I do less of a stretch, the stars are much reduced, and now I get the colors that I expected to kind of see out of it. So I guess the moral of the story is you never get away with just doing the default operation. Sometimes the default operation is going to mess things up, but it's taken me, like I say, this is I think 4 years ago when I did this. So it's taken me that long to figure this thing out. So anyway, so it came out better, I thought. All right, and then I also went around, the third part is I went around and finished up this Foxfur Nebula thing that I had done. I'd started a year ago, I guess, and finally got around to getting the subs done. It was 14 hours of exposures. Again, I'm doing my 15-minute subs, and I'm only doing narrowband. And I looked at the different palettes. Normally, you would look at maybe HSO palette and the SHO. So here are the hydrogens in the red, green, blue, and here are the sulfurs in the red, and then the hydrogens in the green. So the one with hydrogen alpha in the red, it looks like this. So it's got all the red everywhere, kind of like you expect. So it kind of came out interesting. The sulfur is the green, so it's making this orangey kind of things here. So that was nice. The other one, the SHO, that normally I don't like the SHO palette, but when I did it, I thought it actually kind of came out nice. And it really did accentuate much more where the green is, that's the H alpha, and now where the yellow is, that's the sulfur. So it's very clear that this zone in between is a lot of H alpha stuff. The sulfur is all in this furry stuff down in here. So it really does kind of point out differences in where the different elements are in this nebula. So you know, this is more of my normal kind of picture. So at least I kind of vaguely know what I'm doing there. But anyway, I thought it came out kind of interesting, kind of nice. So there's that one, and that's it. Okay.
That is interesting. How long when you start on one of these? How many hours are you putting in, or are you talking weeks of hours?
For the collecting the data, you mean?
Well, collecting and then processing, and I mean, you know, mine. I'm taking my T7i in the field, taking my photos, looking at them, getting them home, and I may spend a minute or two on each one at the most. To get what I have.
Yeah, you're just doing a single exposure, right?
Single.
You're not stacking.
I'm not stacking, and the only playing I do is with a.
So for the collecting, there's 14 hours of exposures. Well, that's not strictly true. There was more than that. There were 14 hours of exposures that I kept. So each sub is 15 minutes. So there probably were 18, 20 hours of actual exposures. And a lot of the ones, they don't work very well or something. I don't like it, so I throw it out. Although it's much better nowadays. But anyway, so it's 14 hours of actual exposures. The processing on it for this kind, because I have this process down reasonably well. So I spend probably 2 to 3 hours maybe, I don't know. Because the one reason it takes so long is when I start, I say, well, let's see, do I want to do the HSO palette or the SHO palette? Or do I want to do an HOO palette? So I end up in parallel processing various streams based on decision points. Well, I don't know if this will be better or that'll be better. If I do RGB and then narrowband, well, do I want to add the narrowband in? Do I not? Do I only want a narrowband? Do I only want the RGB? So I often end up with 4 or 5 images that I do in parallel. So that's one reason why it takes, I probably spend, like I say, 2 to 3 hours, maybe. I don't know. Because you try something, you try something else. There's a lot of back and forth trying. The first half of it goes pretty quick. Calibrating the images and aligning the images and stacking them and all that stuff. That's all fairly quick. It's the stretching and bringing out different areas of nebulosity and curves and levels and those kind of things that I spend a lot of time going back and forth. And plus, a lot of times you get down into your process and all of a sudden you realize, oh, somewhere I did something, and all of a sudden all the stars have got halos. And then I got to back up, 6 steps and figure out what I did to do that. And, oh, I didn't notice it at the time. And then you have to repeat and all that. But I've gotten better at using PixInsight, so it's easier to redo a lot of those things nowadays. So anyway, it takes a while.
And when you're taking your exposures, those 14 hours, I presume that's multiple nights of viewing.
Multiple nights.
Are you doing it from
this
home?
case, multiple months? I think yes. This is my observatory at home. Oh, okay. I no longer have a portable setup. Everything is through here. So yeah, but yes, this is probably 7-10 nights of, it goes for whatever, 3, 4, 5 hours in a night, and then that kind of thing. So yeah, it's several nights. definitely. Yeah.
Yeah, I'm too old and haven't been in amateur astronomy for that long. There are too many things. I've got the Messiers down pretty pat. I'm looking next at the Herschel list, and I'm too old to try to take one object for a week at a time.
Yeah.
Probably die before I get through the list then.
Yes, this is not the kind of thing for trying to make 1,000 nebula or what. Yeah, this no, it doesn't work that way. I mean, there are people that will do very, just a quick short thing so you can recognize the object, but they don't get ridiculously carried away like I'm doing now with these.
Well, the nice thing is that I can't go outside. I melt. You know how sugar is. I melt when I try to set my telescope up outside at the house here.
Yeah.
I don't have a nice little dome or anything that's air conditioned.
Yes.
So
my dome, I have 2 air conditioners and a fan. 10-foot by 10-foot building, and with those 2 air conditioners and the fan working in there, I can generally keep it to 90 degrees or lower.
take a sweater.
Huh?
Take a sweater.
Yeah, it's really obnoxious, some of the thing, because I worry about all the electronics in there. So during the day, it'll get to 90. At night, external temperatures will come down to 95, maybe 90. So they'll get it down to 72 overnight, maybe. But yeah, and I run it from in the house. I run it remotely, so I don't have to sit out in there while it's doing all this. And I run ACP, so I can kind of set up a plan and say, take a bunch of exposures, and I can get it going hopefully by sort of 9 o'clock at night. And then it runs, takes the exposures, and does all the focusing and all that. And then it automatically shuts the observatory down at typically 4 in the morning or something. So I don't have to stay up all night and do all that.
Well,
So
what fun is that?
Well, it's good because I get up at 5:30 to go play pickleball. And
Okay.
Stay up overnight and then go play. Yeah, that's a problem.
There's only one reason I get up at 5:30 in the morning, and that's only. No, well, we won't go into it. It's a guy thing, old guy thing. I get up at 8 for my coffee and read the paper, and then maybe think about doing other things.
Yeah. So anyway, yeah. So it's all done. A lot of it's automatic. So I've got that down to a routine by now.
Do you have a second scope set up so that you can just wander around the sky while this one's doing all the work?
Well, I do. They're on the same mount though.
Okay.
I have 1 mount and 2 scopes. Like this is off my Takahashi 106, and that's piggybacked on a Celestron 11-inch. So I can image off of either one, but yeah, I can't take one and go somewhere while the other's doing this. No. In fact, for the planetary thing, I've been using both. It turns out with that little camera, your field of view is crazy small. It's like 6 arc minutes by 4 arc minutes. So trying to just get the planet to show up is kind of a pain. So I use this camera, the wide field camera, to get Jupiter, kind of centered. And then I go to the other one, and then if I can kind of get it onto the chip eventually. But yeah, that's a pain. With that, the planetary thing is very strange because that thing is so small. I can't do plate solving because it's such a small field with the camera. It doesn't get enough stars in it to do plate solving. So I'm used to my software being able to figure out exactly where it is in the sky and get the target centered and all that stuff. But this one doesn't do that.
Well, interesting. That gives us all a goal. I guess if I should live long enough, I might even get into this. I've got a nice ZWO and Hyperstar. I just need to learn to use it. Anybody teach classes?
Yeah, that's where I'm trying to figure out how. I've got most of it more or less figured out, but especially the focusing is a problem, and I don't really understand. For example, all these guys say, yeah, they focus on a star and then move to the planet. But for some reason, they think focusing on star isn't good enough when you're on the planet. So then they manually focus once they're on the planet. Why isn't the star good enough? I mean, I would have thought a star would be better than, they're just kind of visually trying to focus and see the stripes on Jupiter or something. Well, the stripes are jumping all over the place. Seeing is bad. You know, I'm having trouble seeing how you could do this manually at all. But almost every one of them says, oh, you have to focus manually. And you have to learn to do that. Well, I'm not learning too fast of that. It seems like I put it where I know the star focus is. I know my critical focus zone is like 100 steps on the focuser. So I'll back it out 100, or well, 200, and then step through, say at 50 steps, and I'll take whatever, 8 images that way. Not obvious to me which one's in focus. You know, I can't tell. There's something structurally wrong there. I don't know what it is.
Well, I think you've done a good job. And I appreciate your presentation. So hopefully you'll have an update next month of a new object. Or wait, oh, I'm sorry. This is work in progress, right?
Yes, it all is. Okay. Are there other questions? I can't look at questions here. Is that
Okay,
right?
I'll pull them up and say question for Robert. What is this target?
Oh, this is the Foxfur Nebula. I think this is the what do you call it, the Cone Nebula, and this is, I think this part's the Foxfur. I don't know what part's the Foxfur. And the Christmas tree is this part. There's the base of the Christmas tree, and there's the tree.
Oh, if you turn your head sideways, you can see it. Yeah.
Yes, it's sideways. So the Cone Nebula and Christmas tree, and then I don't know what. If the Foxfur is really the whole thing, I don't know what that is. But it's that area of the sky.
Okie doke. And someone else had a question, what type of camera I was using. Mine is a Canon T7i, just a DSLR. It's not had the filter, protective filter taken out. So I lose a little bit of the color range, or the H alpha, I guess, maybe. I could have it modified at great expense, but why not just buy another camera? Spend the kid's inheritance. Well, thanks again, Brew. I appreciate it. And
right.
we will now move up to our premier presentation. Will Oldroyd, as in an old Android or what have you. He is a PhD candidate, unless you've already gotten your PhD in the period of time that we've been in communication. I don't know. When do you think you might have that, Will?
So I actually just took my written test to get PhD candidacy today.
Oh.
And so I'm in the process of my qualifying exams, and hopefully it's 2 more years to get my PhD.
Jiminy. Well, Will is from NAU, came down from Utah with his wife and son, and is in the School of Astronomy and Planetary Science. And he studies things that are beyond Pluto in the outer regions. So he is going to talk to us tonight about what, Will?
The search for Planet X.
I knew it. I'll let you take the helm here. Can you grab the screen from your...
I think so.
Excellent. You're on the roll.
Okay. So yeah, I'm going to be talking about the search for Planet X today. I'm super excited to be here. I already love your group. Those are awesome presentations. Super cool stuff. I don't get to do nebula very often, or star clusters, so they're always fun to look at. A little bit more about me. Here's a picture of me with my wife and son. He's 3 right now and super cute. Loves to draw me pictures of planets or orbits. Great. Anyway, we really like to travel. So up here is a picture of me and a statue of Albert Einstein in Bern, Switzerland. This is where he worked in the patent office and figured out basically all of physics on the side while he's bored. So that was pretty cool to go see that. I also love to play chess. So here's me and my wife playing chess on this giant chessboard we found in a park also while we were there. I love hiking. Here's me at Delicate Arch at Arches National Park in Utah. And I love grilling delicious burgers.
I like
There's some
delicious
more about
burgers.
me. Yeah, they're great. Awesome. So jumping right into it, from ancient times, astronomy has been one of the most important disciplines in the world. They used astronomy as prehistory even as kind of a clock and a calendar to know when they should plant their crops, harvest their crops, when they should go to war, when they should have big celebrations. Basically everything they measured using the stars to tell them when they should do things. And they knew the sky very well. They knew the constellations, and particularly the planets were very important to them, and the way that the planets moved through the sky and lined up with things was very significant for them. And so this was the state of astronomy. It was this predictive tool to know how to live the rest of your life up until about the 1600s. And so in 1610, Galileo had seen that someone built this telescope and didn't do a really good job, and so he decided he was going to build a good telescope. So he was the first one to build a good telescope, and of course, the first thing he looked at was the heavens. He discovered that Saturn has ears, because he didn't know what they were, and so he found the ears of Saturn, which are the rings. He saw that Venus could have a crescent phase like the moon because it's interior to us, and that these are really worlds. And most interesting to me is he discovered the 4 Galilean moons of Jupiter. And that was really the first new planet type object that was discovered in our solar system, these moons of Jupiter. So here are close-up pictures taken by spacecraft. We've got Io, the volcano moon. Europa is an ice moon, as is Ganymede, and Callisto is a heavily cratered ancient rocky body. Super, super cool worlds. And now there are like 79 known moons of Jupiter, and we keep finding more. It's amazing. Fast forward 150 years-ish, just over 150 years, people have been using telescopes this whole time as a tool for astronomy since then. And so William Herschel and his sister Caroline liked to look for new comets in their backyard. This is a pretty impressive backyard telescope that they have here. In the daytime, he was a composer and musician, and at night he was an astronomer. And as they were looking for new comets, they found what they thought was another new comet, and it turned out to actually be the planet Uranus. So here is an image from the Keck Observatory, a 10-meter telescope on top of Mauna Kea in Hawaii, showing really nice view of the rings of Uranus and how it's tilted on its side. Super cool planet. Anyway, this discovery was the first new planet in our solar system. For thousands and thousands of years, the classic planets that had been known, Mercury, Venus, Mars, Jupiter, and Saturn, were the only planets. They were the wanderers that moved around through the sky, which is what planet means. And so a new one was a huge deal. And of course, Herschel tried to name it after his patron who was funding him, and it ended up being called Uranus. So then, only a few years later, about 20 years later, another astronomer, Giuseppe Piazzi, who was an Italian astronomer, discovered another planet. And this is the planet discovery that no one remembers, because the planet he discovered was the asteroid Ceres, which is the largest asteroid in the asteroid belt. Now it's classified as a dwarf planet, and we'll talk a little bit about that later. Here's a really cool up-close image of this salt deposit taken by the Dawn spacecraft that was there a few years ago. Anyway, so he discovered this new planet Ceres, and he only could observe it for a few days before it went behind the sun. And then for 6 months, it was behind the sun, and when it was supposed to come out, no one could find it again. It was lost. And it was this big debate. People are calling names and things like, oh, you didn't really find anything, or how come we can't find it? That's too bad. And there's lots of discussion and heated debate over this. Is this a real planet that you found? And so a 24-year-old mathematician, Carl Friedrich Gauss, saw this as an opportunity to use his mathematical prowess to figure out what happened to this new planet Ceres. And so he essentially paved the way in the developing of modern orbital dynamics, using all sorts of mathematical tools to do approximations and calculate from a very small amount of data points to figure out where in the sky Ceres should be. And roughly 1 year later, Ceres was recovered based on his mathematical calculations, very close to where he had predicted. And so this was the first big win for using mathematics to predict astronomy since Newton and Kepler, predicting how planets moved in general. But this is, how can you take what you see and translate that into where it should be in the future? So predictive mathematical astronomy. Carl Friedrich Gauss, super cool, awesome guy. A few years later, 45 years later-ish, we have 3 more astronomers. Leverrier, and Adams here were both mathematical astronomers, and they were looking at the position of Uranus as it's moving through the sky. I noticed that it was consistently off. And based on that consistent error in the measurement, they predicted that there should be something else big out there that's moving Uranus away from where it is predicted that it should be. And that something's probably a planet roughly the same size as Uranus. And so Leverrier over here did the calculations for where it should be and told his friend over here, who was an observer, where to go look. And the same night he found it. He's like, oh, it's right there. Discovered a new planet. Then they discovered Neptune. Super amazing. And so this, now we're into the first time using mathematics of where another planet is and how that planet's motion is different from what you'd expect. The perturbations or changes in the orbit from another body to find that new planet. So cool. I love these stories. And from there, that kind of was the precedence of, okay, this is how we're going to continue to discover new planets in our solar system. A really exciting topic. And so Percival Lowell up at Lowell Observatory did all of this mathematical prediction based on the positions of Uranus and Neptune, and he determined that there should be another planet in our solar system. And he called this planet Planet X. And now his Planet X, he predicted roughly where it should be, and he hired an enthusiastic farm boy to come in and do all of these observations, and that farm boy is Clyde Tombaugh. And so what Clyde Tombaugh would do is he'd come in with this big glass photographic plate, and he'd set it in this back slot here of the telescope, and I think it might actually be in this other picture. Here's me by his telescope. So he'd take this big photographic plate and he'd put it in the back of the telescope, and he'd do exposures roughly an hour long or longer, just so he could see really deeply into the solar system past Neptune, which is very impressive to see out there. And he'd do this, and then in the dark, he'd very carefully take this plate, go and develop it in the dark room, and then he'd take another one and do another exposure of the same spot in the sky. And he'd do this over and over again all throughout the sky. And when he analyzed his data, it was on these big glass plates. And so he built or had built this really cool machine. It's a special type of microscope called a blink comparator. And so he would have one plate on each side and a switch that would switch the microscope back between the two plates. And so he'd scan along the plates, and if they looked the same, then he would keep going. And what he was looking for was a tiny little dot that was moving just a little bit. So this dot moves like over here, from there to about there. So one tiny dot that moved a little bit, and he discovered Pluto. After 15 years of observing, looking where Percival Lowell had predicted, and it wasn't there, and it wasn't what Lowell expected at all. And this was after Lowell had died as well. So Lowell died not knowing about Pluto and convinced that there was this planet X out there. Well, after Clyde Tombaugh discovered Pluto, there was all this excitement about it. It was, we found another planet in our solar system. It's amazing, so cool. Here's an image from the New Horizons spacecraft that did a flyby of Pluto a few years ago. Super amazing dynamic world. There's ice, volcanoes, huge nitrogen glaciers, sand dunes made of carbon monoxide ice. This is an amazing place. And the more we learn about these planets, it's amazing to see what we find. So from there, that it kind of wasn't what was expected. So Lowell had made this prediction, and that's not where Pluto was found. Pluto was a lot smaller than was expected. And astronomers have since gone back and seen that the error in the measurement of the position of Neptune and Uranus was big enough, because they couldn't measure accurately enough, that's where this prediction came from. So it was just in measurement error. But nonetheless, Clyde Tombaugh found Pluto. And so then for many years, there wasn't another major planet discovered in our solar system. There were a lot of asteroids that were being discovered throughout this time. Basically, since Piazzi found Ceres, there are asteroids that have been discovered. But then in 1992, Jane Liu and Dave Jewett discovered a new group of objects in the solar system, and it's the Kuiper Belt. Now, this is like the asteroid belt. It's mostly icy and rocky bodies that orbit beyond Neptune. So Pluto is one object within the Kuiper Belt, and right now we know of well over 3,000 that we've found so far, and there are definitely more out there to find. The Kuiper Belt is roughly 1.5 billion miles across in the ring distance here, and then there's more kind of scattered outward, but the main belt of it is 1.5 billion miles across for the ring thickness. All the way around is a lot more. So they discovered this, and then 1995, Kalos and Mayer made another huge planetary discovery, this time not in our solar system. They discovered planets around other stars, exoplanets. And this opened up a whole new discipline in astronomy, which is exoplanet science. There have been over 4,000 exoplanets around other stars discovered so far, and we're only going to discover lots more in the future. They just got the Nobel Prize for this discovery this last year also, which is pretty awesome. Moving forward and going back to the Kuiper Belt here, astronomers started discovering things like Pluto. So particularly this group here, Mike Brown at Caltech with Chad Trujillo, who's now my advisor at NAU, Dave Rabinowitz, and Mick Schwam. There were a few others as well, but they were the main ones. And they started finding things that were about the same size as Pluto and in the case of Eris, even more massive. So they discovered Eris and Maki Maki and Haumea, and this one's now named Gong Gong, and just several other Pluto-like objects out there in the solar system, in the Kuiper Belt and beyond it. And this discovery was kind of shaking up the solar system astronomy community, because the question is, okay, now do we have 15 planets or 30 planets in our solar system? Or do we have to redefine what a planet is in order to really classify them differently? And so in 2006, the International Astronomical Union voted basically to create a new class of objects in the this is how we define objects system, called a dwarf planet. And basically, a dwarf planet, there are a few criteria, but the main one is that it's a lot smaller than the other planets. Pluto is a lot smaller than our moon, and all of these other things are smaller than Pluto. So it's very interesting and kind of sad for Pluto and those other now dwarf planets that got demoted, but at the same time it made a lot of sense because we're going to keep finding more of them. And so particularly in Flagstaff, this is interesting because that's where Pluto was discovered. And so a lot of the time in Flagstaff, you have to be very careful talking about dwarf planets versus planets, because some people will get heated about it and like, no, Pluto's definitely a planet. They're like, yes, it is. It's just a small one. So it's, yeah, and still love Pluto and the dwarf planets. And that's what I focus mostly on, are these large small bodies in the outer solar system. Then in 2014, my advisor Chad Trujillo and his collaborator Scott Shepard discovered another one of these dwarf planet class objects named 2012 VP113. All of these bodies get sort of license plate numbers before they get named, and this one still has a license plate number and not a name yet. It'll probably get a name eventually, but it doesn't have one yet, which is kind of fun. And anyway, this object was really interesting because in the outer solar system, there's the Kuiper Belt out there, and then there are kind of these scattered objects. And then there are a few really scattered objects called extreme TNOs, or extreme trans-Neptunian objects. And they're kind of the weirdest, most crazy orbits out there that aren't comets that come in once and are gone. So there are those objects. And then there was Sedna, which is way over here by itself in a really crazy orbit. It never comes close to Neptune. All of these other things come kind of close to Neptune, but this one never does. It never gets anywhere near Neptune. And then VP113 here was interesting because it was like Sedna. It meant there were two of these weird ones way over here. And so looking at the weird ones, Trujillo and Shepard made this plot. And here they saw on the bottom is semi-major axis, which is distance from the sun. And here is the argument of perihelion on the y-axis, which is basically the angle around where they come the closest to the sun. So everything has a closest approach to the sun, and this is where it is. So 0 may be straight ahead, and then as you go up to 180, it's going this way, and go negative 180, it's going the other way. Anyway, most of the things out there in the Kuiper Belt were kind of random. They all had angles that go all the way around, but all of these more extreme ones and the two really weird ones in red here were all in a line. And that starts to raise red flags, like, why are these all lining up? And part of the reason why that's a big question is because over really long time periods, as objects orbit the sun, their orbits will precess, which means they kind of move like a top, where you have the whole top spinning around, and that's the orbit of the planet. But the top of the top will kind of do this thing, this kind of wobble around. And that's exactly what the orbits do too, as long as there's nothing to keep them where they are. Now, if you have something to hold them in place, like a planet, say this bluish, this cyan orbit here is a planet, and this pink orbit here is your asteroid or your dwarf planet that's orbiting around here. So if there's a planet orbiting around it, it'll kind of shepherd it into this region. And here's the star, which is the sun, and the blue circle there is the orbit of Neptune. So these are things that are really far away. But as this planet is trying to precess, it kind of gets pushed back into this wobble inside of the circle that is, or the ellipse, that's the orbit of the planet. Now, the same thing can happen if it's going the opposite way and poking out. It can still get shepherded just like that. And that's called libration, or it's an oscillation back and forth. And so Trujillo and Shepard showed that if they had a planet if they simulate a planet with this new object, it would go back and forth just like that and keep it in this line here, pretty much. Keep them all lined up. And it looks something like this when you look at it at the actual orbits. It's these crazy spaghetti orbits here. So, this dot here in the middle is the sun, and this circle here is the orbit of Neptune, which is 30 times further than Earth from the sun. So these orbits are gigantic orbits that go so far away, and we discover them when they're basically as close as they'll ever get to the sun. That's when we discover all of them. Because out here, our technology is not good enough to discover an object that's that far away. This is like 1,200 times as far as Earth-Sun distances. It's just amazingly far away. But anyway, they more or less follow this rough line here. And so as all of these bodies are orbiting, they get bounced back and forth and line up in the solar system. And this idea that there was a planet that was sort of shepherding all of these other dwarf planets and Kuiper Belt objects, minor bodies around in the solar system, the idea caught on and was incredibly exciting. And so in the past 6 years, over 100 papers have been published on this idea that there's another planet hiding out there in our solar system that we need to find. And in Flagstaff, we always call it Planet X. And we're very careful to call it Planet X. But everybody else calls it Planet 9 as another planet. But we can't call it Planet 9 because that's Pluto. So Planet X. Okay, so the next question is, if there is another planet, a Planet X, out there in our solar system, and we know it's moving around these other things in a predictable way, why haven't we found it yet? Shouldn't it just be just like Neptune was found a long time ago? And the answer is really because it's far away, which seems kind of like a weak answer. We can see galaxies that are thousands and thousands of light years away, but how come we can't see a planet in our solar system? And it's because it's really small. It's probably smaller than Neptune, probably bigger than Earth though. So it's probably like a mini Neptune type planet, but it's really far away. And so now I want to talk a little bit about the scale of the solar system in terms of something that a lot of people can relate to, which is a football field. And we're going to have not enough football this year, so I figured we'd have it more right here. This analogy here that I'm about to share is developed by a NASA scientist turned YouTuber named Mark Rober. And basically he was a NASA scientist, helped build the Curiosity rover that's going around on Mars. And then his YouTube channel, like science YouTube stuff, was so successful that now that's his job instead. So he came up with this, and it's a cool analogy. So if you have a soccer ball and pretend that's the sun, and you stick it on the goal line of your football field, then you can use ordinary around the house things to describe the size of the planets and the distances on the football field. So if we look at Mercury, it's the size of a fleck of pepper at 10 yards from the soccer ball sun, which already seems pretty far for this planet that's whipping around there every 70-ish days. Venus is the size of a head of a pin, and it's at 18 yards away. And our home here on Earth is also about the head of a pin at 26 yards from the sun. And that's a lot further away than any drawing has it, because in drawings you always have, here's the sun, here's the planets, all in a row, and they're all the wrong sizes comparatively, and they're all the wrong distances. But here we start to get bigger distances, as Mars is also a fleck of pepper at the 40-yard line. And then here's the asteroid belt right here. But then we have to move to a second football field. And about 135 yards away from the sun is Jupiter at the size of a grape. Then Saturn is right about on the next football field. 2.5 football fields away is Saturn, slightly smaller grape. Uranus is about 5 football fields away, and it's the size of a pea. And Neptune is almost 8 football fields away, also the size of a pea. So already our solar system is looking pretty huge here. We've got a soccer ball sitting on the goal line, and then like 3 parking lots over is Neptune orbiting the sun. So already we're really far away. And this comes to the reason why we haven't found planet X yet. Because 300 football fields away is where planet X is. And that's really far away in our solar system. For comparison, that's where Neptune is. And the sun is right here on the left side. You can't even see it because it's so small. So this is about a 5.5 hour walk. If you're just walking at a brisk pace, maybe a slow jog, and it's like several miles away in terms of our analogy here. And so this is already tens of billions of miles away from the sun. And that's far enough that you basically need to know exactly where it is to be able to find it. And even then you need to use the biggest and best telescopes in the world, and to be staring at it for probably more than just a 15-minute exposure. You probably need at least an hour or more of exposing just to get an image resolved of this, if you know where it is. And because we don't know where it is, that's one of my main goals, is how can we constrain where this thing is? How can we find it? So I look at this feature in the outer solar system. It's called the gap, the perihelion gap. So here on the x-axis is perihelion, and that's the closest approach to the sun. So if you've got a planet or a dwarf planet or an asteroid here orbiting the sun, and the sun's right here on my nose, and it's orbiting in an ellipse like this, then the closest approach is going to be right here. And so that's what we've plotted here on the x-axis. And then the eccentricity on the y-axis is how stretched out this orbit is. So you remember some of those really loopy stretched orbits and that other thing. Those are way up here near the top. So in this figure here, we've got all of the classical Kuiper belt down here, some of the scattered further up. Here are the centaurs that go in between Neptune and Jupiter, back and forth. And then here are those extreme objects that are the really crazy ones. And then over here are the Sedna-like ones, and there are 3, Sedna, VP113, and this one now has a name. It's Leleaukuhonua. named after something Hawaiian, because the telescope that found it was in Hawaii. Okay. Then in between those weird ones that are way out there and the extreme ones that are also way out there, just less out there, is this big gap that's over 1 billion miles wide. And we don't know why it's there really, but it should be much easier to find things in here than it is to find things like Sedna that are way out there. And so the question is, why is there a gap? How can we use that to learn about planet X? And so what I do is I use NAU's supercomputer Monsoon to make tons of simulations. And because it's free for NAU students and faculty, I have a lot of resources at my command here, and I've used over 1 million compute hours. So that's like you running your laptop for 1 million hours straight to do this. Because it's on a supercomputer, I can do a lot more at the same time. And it's really fun to use. What I do is I put the sun in there, and then the planets, Jupiter, Saturn, Uranus, and Neptune. The terrestrial planets are negligible in a simulation that's this far out. And so they can be ignored, which is amazing to me. But then I put in a ton of test particles. Lots and lots of things that represent asteroids. I want to see what happens when we add planet X. So stick planet X way out there, a guess for where it might be and what its orbit is, and see what happens to all of these particles. So when we do this, here is a simulation with no planet X, and I'm showing the same perihelion versus eccentricity that I was showing in that last figure there. So they all start down here, and as they interact with Neptune, some of them get scattered up here, which means stretching their orbits out, but nothing really comes over here by the gap, or especially way out here near the crazy objects. Here's a heat map to kind of visualize that better. All of these green dots are the real objects out there in the solar system. Red means there's always particles there in the simulation, and blue is almost never. And so white is never. So here we see that as these things interact with Neptune, they come up, and that's about it. Some of them come up, some get sent inward to be centaurs, some hang out down here, but nothing really comes and looks like these other objects out there. But then when we add planet X in there, they all start flying out this way. So as Neptune scatters these ones up, planet X pulls them out, and they get caught in a resonance, kind of like that one that went back and forth, but this time they're going back and forth along these lines, roughly. They go back and forth. And so they move through this gap, but they kind of fly through it as a transition region rather than somewhere where there's never any particles. And so here's the heat map of that simulation again. Objects are scattered upwards by Neptune and then pulled out by the planet. And in the gap, there's a lot of white space and lots of really dark blues, meaning, yes, particles come through there, but they usually come zipping through there on their way out. It's a cool transition region. And so what I'm doing is using this gap as a way to constrain where planet X could be. Now, this type of spur here coming out could be indicative. If that comes up into the gap, then we should see a bunch of stuff in there. And so keeping that out and then also trying to get these up as high as possible, testing lots and lots of different versions of the planet or lots of places where it could be to try to figure out which ones work and which ones don't. So on top of all of these simulations, we are doing this big survey to actually look for the planet. And here, the blue line is the plane of the solar system. So where all the planets are orbiting around their sun is along this blue line mapped onto the sky here. The red hash here is where the galaxy is, and there's lots and lots of things in the galaxy plane, and so it's hardest to look there. So we don't look as much there, but the planet could be there, and then it's harder to find. All of these black circles are places we've looked as of 2018. And so we're continuing to look all over the sky and try to find as many of these extreme objects as we can, because those objects tell us the most about where the planet is, and we also want to find the planet if it's out there. And so we use the Subaru telescope on Mauna Kea. It's an 8.2 meter telescope that shoots lasers, and this laser here is part of the adaptive optics system. And what that does is, as you're flying in an airplane, you're not going to get shot by a laser, but as you're flying in an airplane, there's turbulence that bounces you up and down, and that same turbulence is what gives you part of your bad seeing. And so in order to mitigate that, they use this laser to focus through the atmosphere and measure the atmospheric turbulence, and then actuators underneath the primary mirror of the telescope actually deform the mirror at the same rate the atmosphere is moving to kind of cancel it out. That's amazing technology that allows us to do that. Super cool. And we use that mostly for finding these objects. And then for follow-up, to make sure that we can find them again and calculate their orbits, we use the Magellan telescopes in Chile. These are 6.5 meter telescopes in a beautiful site in Chile, and really nice to observe there. Also the Blanco telescope and the dark energy camera, which is a 4 meter telescope in Chile. All of these telescopes have really wide field of view. So earlier we were talking about things that have a tiny field of view and are hard to work with. We want as wide of a field of view as possible because we want to see as many things as we can. And so lots of these have multiple chips, and we're seeing a huge area of sky, multiple degrees at one time. The other one that we use for follow-up is the Lowell Discovery Telescope, just an hour outside of Flagstaff, down towards Phoenix a little ways. And this one's a 4.3 meter telescope that's really, really nice to use. And it's great for follow-up. It's in a really nice site, and it's close by. So we love using these world-class telescopes because they're the only things that can get deep enough to see it. A lot of times with this telescope, we're stacking several 15-minute exposures, 30-minute exposures together in order to just be able to see a dot. And it's just like how Clyde Tombaugh discovered Pluto. We look frame to frame for a little dot moving around, and that's how we discover new objects and find them. And it's amazing to me that we're still finding new things in our solar system almost every day. And there is so much more out there to find. It's so cool. So in summary, the rate at which astronomical discoveries are being made is accelerating. Starting from Galileo in 1610 up till now, there are more and more all the time, and we're finding new things and new classes of objects that we never even knew existed. There's black hole astronomy being done. There's exoplanet astronomy being done. It's amazing how many new things we're finding all the time. So about 6 years ago, we started finding this evidence that there's another planet in our solar system, Planet X, and it looks more likely than ever that it's out there somewhere. We keep on finding more things that are all fitting this trend. The really extreme ones all fit. And so it looks like Planet X is there somewhere. And we're getting closer to finding it. And hopefully soon we will find it. Thank you.
Thank you, Will. Some questions here. Where is Planet X predicted to be in relation to the Kuiper Belt and Oort cloud?
Okay, that's a great question. So the Kuiper Belt let me come back here to my slide that I had on that. This one right here. So the Kuiper belt is roughly between Neptune, which is at 30 AU. AU is one Earth-Sun distance on average. So 30 times the Earth-Sun distance is Neptune. So it goes roughly from there to about 47. And that's where the Kuiper belt lives. And then there are these scattered objects that go up past it. Then the Oort cloud is mostly scattered comets that, as the solar system was forming, it formed in a cluster of stars, so in a star cluster, and as it's moving there are other stars that are moving things around and throwing things everywhere with gravity. The planets are migrating around, throwing things out, and so some things end up in this kind of cloud that starts disk-like, but then kind of fans out and goes all the way into a sphere around the sun that goes thousands of astronomical units, thousands of Earth-Sun distances. And so that is more of a theory. We haven't observed a lot of these. We've observed comets coming in, but we don't really have too much measure of the structure of the Oort cloud, just the comets that we see. Now, Planet X has been estimated to be anywhere between 300 and 1,000. So it's kind of in the middle, in this mid-range, and that's why these objects, the Sedna-like objects here, are called inner Oort cloud objects, because they're kind of like an inner edge to the Oort cloud, and this one is kind of like an outer edge to the Kuiper belt. Yeah. So these ones, Neptune is in charge, and these ones, Planet X is in charge. The Oort cloud is just left over from a long time ago. Hopefully that answers your question.
We'll have to leave it at that. Is it possible the Vera Rubin telescope will help find Planet X due to the wide field of view?
Yes. So the Vera C. Rubin Observatory is going to be astronomers' best friend coming up in the future here. It's going to find tens of thousands of new things in our solar system. Hundreds of thousands. So it will discover a lot of these objects out here. And with some special analysis, we might be able to find Planet X with it, particularly if we have better constraints on where it is. Right now, it's not very constrained where it is, but if we can narrow in on it better, then the Vera C. Rubin Observatory should be able to see it, as long as it's not closer to the 1,000. If it's closer to the 300, then definitely.
Interesting. A question I have is on your perihelion graph, I see quite a number of what appear to be linear associations of planets down through here. What is that indicative of?
So these are mean motion resonances with Neptune.
Oh, I knew that. Yeah. Okay. What is mean motion
So
resonance?
a mean motion resonance is every time one thing goes around once, the other thing goes around twice, or any number combination. And so this strong feature here is the 2 to 3 resonance. So every time Neptune goes around 3 times, Pluto goes around twice. And that is actually a really stable structure in our solar system. Let me come back here to this slide I had on the Kuiper belt. Get to it. Here we go. So in this one, you can see the orbit of Neptune is this outer white circle here, and this yellow circle is the orbit of Pluto. Pluto's orbit actually crosses Neptune's orbit sometimes because it's stretched out. And because of that, if they ever met in the middle there, Pluto would get wrecked. Neptune would win, and Pluto, something bad would happen to Pluto, and it would be gone. But because of the resonance they're in, with Neptune going around 3 times every time Pluto goes around twice, they never come close to each other. And so they're always on the opposite side whenever this close pass would happen. So if Neptune is right here, Pluto's way over here. And if Neptune's over here, Pluto's way over here. And because of that, it's really stable. And so a lot of objects are safe in that region. In the region next to it, they might not be safe. They might crash into Neptune or be ejected or become one of these centaurs that floats around near Jupiter and Saturn. But those resonances are essentially a stable frequency in the solar system that keeps everything safe, which is cool. And that's basically what happens with these inner Oort cloud objects as well with the planet. They're all captured into a resonance, some resonance or other with the planet, and that's what moves them out. Is they're stuck in that safe zone, and then interactions can keep them going along that line. Super interesting and great question.
Dave Baker is asking, I read that you were part of the discovery of the furthest object yet found in our system. Can you tell us more about your role in that discovery?
Yes. So it was nicknamed Far Out because
how original.
Yeah, very original. It wasn't, so on this graph here, it's probably one of these ones here. So it doesn't, on this particular graph, it doesn't look exceptional, but it was currently further away than anything else we've discovered. So if you look at the orbits, let me go back to those. So on these orbits here, it was probably on its way out instead of, or further away and on its way in. Most of these we find when they're closer. It was the furthest thing we've seen in actual separation distance. And so my role in that was doing the follow-up observations, and that was at the Magellan telescope down in Chile. They were initially discovered here on Subaru, I believe. I would have to double check on that one, but I think they were. And then we did follow-up at Magellan to find that we could find it again and figure out its orbit. And that was my role, was doing those follow-up observations. After that one was discovered, like only a few months later, our collaborator, Scott Shepard, found another one that was even further away and named it, or nicknamed it Far, Far Out. And so the one that I helped recover is no longer the most distant one that we ever found, but the second.
I would take it. And do you think that there is also something beyond Planet X?
I'm sure there is more to discover. Every time we look further, we find more. And every time we build better tools, like Galileo building his telescope, or like us building the Vera-C-Rubin Observatory, we're going to find more. And that's one of the things I love about astronomy, is you never run out of cool new discoveries. There's always more to find out there, and it's always amazingly cool.
I got to understand. Is Planet X, do you think, going to be a super Jupiter, or is it just going to be something more in the line of Pluto or a super Pluto, or what size do you estimate Planet X to be?
So this Planet X, the one that has the gravitational signature that points to shepherding these orbits, the one that we're looking for, is in the sub-Neptune mass region. So probably roughly 5 to 10 Earth masses.
Smaller than not expected.
Yeah, so it's amazing that a little planet, bigger than Earth, but smaller than one of the giants, could have this much effect.
That far away.
Yeah. And it doesn't have very much effect over short time scales. Thing I forgot to mention is these simulations that I ran were 4.5 billion years long. So the age of the solar system. So over really, really long time scales, these things move. But at any given time, they're all frozen in place, just like this snapshot here.
Another question that was asked, do you think New Horizons will be able to assist in any of this?
Unlikely. The New Horizons would have to be very lucky to be of much help. If we found the planet, New Horizons, if it's on the right side of the sun, then New Horizons could potentially observe it and get more information about its position and do better measurements. But unless New Horizons serendipitously is going in the right direction towards Planet X, it's probably not going to help much in the search, other than maybe measuring the gravity of Pluto and some other things that could be used as constraints for where it is.
Okay, if Sedna and other TNOs are in the Oort cloud, would Planet X also influence the orbits of long-period comets? And could those comets be another way to search for Planet X?
Yes, is the short story. It gets really complicated. We don't know the exact extent of the Oort cloud. The Sedna-like objects have been termed inner Oort cloud objects, but they might actually just be a separate third population. We've got the ones by Neptune, the ones by Planet X, and then the Oort cloud. And so it's a little bit of a confusing term. That being said, yes, Planet X is definitely going to affect long-period comets. And there has been some work done with that, as well as with the short-period comets and their evolution. But it gets really tricky, and we don't quite have enough information to make it work yet.
Well, speaking of not a lot of information, what do you think that is Planet X expected to be a gas giant or rocky planet?
So that has been thrown around back and forth quite a bit, actually, whether it's a super Earth or a mini Neptune. And one of my collaborators actually is working on atmospheric modeling based on its mass and location, and it looks like it should be a mini Neptune rather than a super Earth. So probably not going to be able to land on it, but that's okay.
We'll leave that for someone else to worry about, because I don't know how you get a spaceship out there that far.
Yep.
Anybody else have questions they want to propose for Will? Okay, well, Will, I do appreciate it. And let me see if I can, here we are, back to our ream of people. That was quite interesting. I'd always heard the discussions about Planet X, but Sedna was kind of, that's kind of interesting that it's like, it's almost Planet X now. And it's just like, it's like you say, far out.
Yeah, it's one of the biggest mysteries of the solar system that we need to solve next. And that's what I love about astronomy, is it's one big mystery after the other that you have to put together all the clues, almost like Sherlock Holmes, to be able to deduce what the answer is.
Well, the math with this, I mean, I had to go an extra semester to get my calculus out of the way. So I can't fathom the math that goes into the program. Do you do the programming, or do you have an undergrad that does your programming for setting up these models?
So I do all the programming, but I also use some pre-built tools that are amazing. The integrator that I use that does all of the gravity calculations is called Rebound, and it's a very, very nice tool that has been put together by a couple dozen people working on this as their main focus to build this amazing tool that I use. So they stand on the shoulders of giants.
Well, but of course, yes, sure. They are like they're giants out there. Come on. The science on this is just always baffling to me. Even like Brew was doing with his, your flats, and then you have to do your you're scavenging and then stretching and whatever. I don't know. It's kind of like yoga. I don't understand how it works, but evidently it does for some people. So, but yeah, it is fascinating. And I mean, being a retiree, people expect you to just sit at home and watch Price is Right all day long and vegetate until you die. But like you're talking about astronomy and looking at the technology. I mean, my background in my degrees, undergrad and grad degrees, are science, and astronomy was a latecomer to me. And it's just like, wow, I wish I would have really been more attentive in my math classes because it's all about the math. And it always, I can't fathom the gravitational aspects of how you could see something affecting planets so far away. Oh no, it's got to be something there because we're seeing that something perturbated that we just can't explain. It's like, really? It's like, wow. Yeah, I just the book Parallax about just about the discovery of a lot of the astronomers that you were talking about in their goal to figure out how to measure the star distances. And it's just like, wow, that was so intuitive, and it's so much math. So it is, yeah, it's all about the math and the Benjamins. Yeah.
Yeah, exactly. Like Isaac Newton invented calculus so that he could do astronomy.
Yeah.
Basically.
And I have, there was one other question I can't think of. Oh, the James Webb. I've heard that there's this big telescope, space telescope, going to be built called the James Webb. And is it going to be any help to you guys if it ever launches?
So I've seen a graph of predicted launch dates for James Webb. Mm-hmm. And when those launch dates are released, and they're converging, and so it should eventually launch in the next few years based on that. James Webb.
I'll help you out there because Roger Windhorst is going to talk at SAC in exactly EVAC in 2 weeks on the James Webb.
Oh, excellent. Excellent.
Yeah.
I will tune in.
October 31st, 2021 is the latest.
But I hope to live as long.
Yeah.
Well, let's see. Were there any more questions down there? No, I don't think there are any more questions. Will, we do appreciate your presentation. Brew, appreciate your presentation. And Paul, anything you had to say?
Not really. If you haven't renewed, if you're a SAC member but haven't renewed for this year, go ahead and do so.
Okay. Will, Paul is taking your advice and trying to do that 5 miles. You're
going to make it.
The Oort cloud is, or Sedna, or Planet X. So
standing at the treadmill desk hurts after a while, so you have to do some walking.
I thought maybe you're just generating electricity. I couldn't tell if the lights were coming stronger or dimming or slowing down. But, you know, it's all about the technology. Okie doke. Well, I think that's it. Unless anybody else had anything, checking the chats, anything, accolades, and I think that does it. Again,
thank you so much.
We will be in contact in a little while. And this is all for tonight. Thank you all for participating and watching. Meeting's adjourned.
Thank you so much. Yeah.
Oh, it is? I'm sorry. Yeah.